Okay, it started.
All right, that looks good. So I'm not a judge in the competition. I'm a safety reviewer. So nothing that happens in the safety review has any bearing on your score or anything like that.
Okay.
You know, I do have the option of not launching your rocket if I don't really like it all that much, but otherwise I don't have a way of influencing the score. You know, I just want to encourage you to ask about anything that maybe you have questions about, and you know that you might not want to tell a judge, but I'm not a judge, so you know I'm kind of here to help make sure you have a successful and a safe flight. So
Okay.
um, sometimes I feel like teams are trying to impress me, and rather than just telling me what I need to know from the point of view of looking at safety. So I guess the first thing I would just say is if you can, you know, well, do you have any questions that you want to raise first before we launch in, or?
Not initially. I know we have a kind of a PowerPoint that was detailing our project, so I can dive into everything in that aspect if you wanted to see that, and then we could kind of go through step by step for all the
Okay.
components.
Do you have the rocket with you to show, or?
Yeah, so we have plenty of components. So we have our avionics bays, we have a lot of our structures hardware, like our transition module. We have a version of our tip-to-tip layup. We've been struggling with some outside manufacturers and kind of dealing with people outside of the Acronauts to help with our curing process. But we do have one that we've done before, and we're in contact with somebody right now to get that process going. So the one that we're flying isn't here, but a direct replica that we've used and then is here as well. And we just flew one on our liquid engine rocket 2 months ago, so that it has been flight tested as well. So I have that. We have our motors and their hardware, and then our body tubes as well. So
One question I had on your body tubes, I saw that you might be using polyester resin as opposed to epoxy resin.
on our layup,
Yeah, that was listed for the winder on one of the progress reports, and I have not seen that before, so I was just wondering if you were doing that or that was a typo.
no. So our we were working on that, but our X-Winder project didn't come with the timelines that we wanted to. So we actually just ended up going with COTS body tubes for now. We bought off from Mad Cow. That project is ongoing, but it's not going to be going on this rocket itself.
Okay. Well, go ahead and take it away, and we'll just ask questions as you go.
Okay. There you go. Yeah, so I will share my screen as it loads. Yeah, okay. So yeah, starting off, first, I guess I should say my name's Eric Diffendale. I'm going to be the chief mechanical engineer at Spaceport this year. So, we're going to be launching what we're calling Project Eric, or Project Enhanced Recon with an interplanetary cruiser. The interplanetary cruiser is our payload this year, so that'll be detailed later in the slides. But yeah, kind of to detail what this PowerPoint goes over, we're going to be going through just general dimensions and components, our ConOps, our flight graphic, and then we'll go into our overview, just general overview of our SolidWorks, then our simulations, and then each of our sub teams that we have. So structures, composites, avionics, recovery, payload, and lastly, solid propulsion. So kind of starting off with our general dimensions, our rocket's looking to be about little under 19 feet tall. We're doing a 2-stage, so we have a booster overall diameter of 6.15 inches, and we have a sustainer diameter of 4 inches with an overall weight, total rocket weight of 164 pounds, 122 pounds dry. Our booster apogee is around 1,600 feet, but our total apogee is going to be around 29,733 feet with a max velocity of 1,570 feet per second and a total flight time of approximately 90 seconds. Those are all from our Open Rocket and RAS Aero sims. So for recovery, we'll be using CO2 ejection. Our stage separation will be a black powder stage separation though. And then our sustainer motor is an SRAD, angry Listerine propellant, motor classification M2100. And then the booster motor is going to be a COTS N5800, which we actually bought off of Harry Spears. So,
I'm a little surprised to see a booster apogee of 1,600 feet. That's going to very much surprise me if that's the case.
Mm-hmm. So it was a little low from what we saw. We ran some sims further, and it was sitting around between 16 and 2,500. But the sims we had here right now were at 1,600. I know we have had in the past that we've kind of simmed our boosters a little low just from what we've gotten generally, but then our total apogee comes out generally correct. When we flew our Emergence 3 rocket, which is a different rocket, our booster was a lot lower in apogee was higher in apogee from sim to actual rocket, but the total apogee came out the same as well. So that's something we've been playing with to try to figure out what's going on there.
Okay, if you have a graphic later that sort of shows the altitudes, let's just look at it, and with respect to that number when we get there.
Okay.
I would have expected an apogee for the booster of 5, 6, 7,000 feet. Mm-hmm. So when I see 1,600 feet, I'm suspicious that there's an issue. So
our booster motor is going to be a 4-inch diameter as well. So it's not going to be a 6-inch. It will be a 4-inch, but
right.
But okay. I know that the COTS motor itself will be at the very end. But if you have questions, our sims will be earlier as well if we want to look at those. Did you guys get the Open Rocket sim that we sent over as well? Did that happen to go through?
Yeah, I did.
Yes.
And I'm glad I asked for it because it showed a few changes over the previous versions that I like. So I was glad to at least get tipped off on that.
Perfect. Okay. Yeah, so we ran some like our basic con ops, going through each of the stages, including our stage separation and then our recovery as well. So that's kind of listed out here, starting with booster ignition, with booster going up to the coasting of the entire vehicle, and then our stage separation occurring, and then descent among each of the stages after sustainer ignites and goes to apogee. We have both of those descents in blue and purple there. So
one question I should have asked a little bit ago. Is Chris joining us for this, or?
I don't think so. I know he got the invitation, but I don't think he'll be here today.
Okay, yeah, FORs are supposed to attend these, but it is what it is. So.
Okay. Yeah, we haven't heard from him today, at least. I know he wasn't at ours. I don't think he was at ours last year as well. But so we have our kind of going off our con ops as well. Our flight graphic for the entire rocket. again, that I know we have booster apogee listed there. We can look at the sims again. But our sustainer apogee is again sitting at that 29,733 feet. And then kind of details how our payload is eventually going to come out of our rocket as well. So, any questions on that?
Well, I'll ask a question on the payload since I'm curious. I suspect you're going to talk about it later, but is that something that is initiated by you after you get to the rocket?
Yes. Yes, it is.
Okay, so it's not going to happen by itself in an uncontrolled manner. You're going to do it.
Yes. Yeah. No, it'll be controlled by us once we find the rocket. Once we actually walk up to the rocket, it'll initiate from there.
Okay.
So then next we can go over the rocket, like the general overview. Again, we're using that N5800, so we have an aero pack on our booster. That booster also includes our tip-to-tip fin layup. And then we'll have 3 centering rings, including the one that the aero pack will be mounting to, along the booster motor. Right above that, we're going to have our drogue bay, which will be attached, we can walk around and see later, to the eye bolt to the top. That's at the top of the COTS motor casing, and then another eye bolt that's attached to the bottom of our avionics bay. It's going to be similar for the main parachute as well. We're going to have an eye bolt at the top of the avionics bay, and then we're going to have an eye bolt at the bottom of our bulkhead that is the mounting surface to our payload bay. So those are going to be our 2 mount points for the rocket for the parachutes. And then that our payload bay is going to be housed inside our transition module, which again will be held in by a couple. One, the transition module itself, and then we also have shims in there that will be screwed in. After that we have after the fin can, or after the transition module, we get to the sustainer, which includes our compressive fin can technologies we've flown a couple times in the past, especially flew it last year, but we've had a couple iterations of it. And then we're using our SRAD blue 98 millimeter motor casing, which will also have an eye bolt on the top that will attach to our drogue parachute, which I know I don't have that labeled here. Our drogue parachute, and then a similar process to the booster, eye bolt on the bottom of the avionics bay, eye bolt on the top of the avionics bay, and then we have an eye bolt attached to our nose cone tip. So our main parachute will be housed in the nose cone. So, any questions on that?
Yeah, on the booster, is that a surface mounted fins or through the wall fins, or what is the?
So they're through the wall fins. We have fin tabs that are about a half an inch thick, or I guess a half an inch in height, that will fillet not only the outside adhering to the body tube, but will fillet the inside as well. So.
Okay. And the still aluminum fins on the sustainer?
Yes. Yes.
What either describe, or you can show me later, what a compressive fin can is. I'm not sure what the term means.
Okay. Yeah, I can. The way we mount our fin can onto our motor casing, we do it in such a way that the fin can is modeled exactly to the OD of the fin can, or of the motor casing itself. But then as we screw it in and put our set screws down the middle, it actually will compress into the fin can, so we don't have rotation. There's another safety component that we have on the bottom of the motor casing that the fins slot into so it doesn't spin, but it's 2 versions of keeping our fins aligned. So I can show that off later as well.
Okay. And the only other thing, I'll just raise the issue now, and you can show me what you're doing later, but I would not want to overlook it. And that is on the eye bolts that are on both of the motors,
Mhm.
and also on the various avionics bays. I'll be wanting to see from unscrewing during recovery.
Oh, okay. Yeah, we use Teflon tape before we put our eye bolts in the screws. So that's typically how we lock our screws in, or our eye bolts in, to our bulkheads and to our motor casings for that matter. So
Okay, well, Teflon tape isn't a retention means for eye bolts. It may make them tighter, but it doesn't retain them.
okay, I can show you what we do later on if you want me to, if that works out
I
for you.
will.
Okay.
Normally, if you're looking at, well, sort of the default process for retaining, a recovery hard point like that would be to use a cotter pin. And it depends upon, what the forward closures look like, whether or not you can use a cotter pin or not. But that's a sort of a positive retention so that the eye bolt can't unscrew as the rocket's falling. Okay.
Okay. Okay.
On altimeter bays, there's an alternate process that you can use. And typically the way that that's done is you'll have an eye bolt or an eye nut on the altimeter bay. And then you take some other hard point on, off to the side on the lid. And, it might be another, eye bolt or a smaller connection of some sort. And then you just take a piece of Kevlar thread or a piece of safety wire and you wrap it around the eye bolt and the other hard point so that the eye bolt can't unscrew.
Okay.
So we'll want to be looking at those things, but if you didn't do that here in advance, you would be doing it at Spaceport. So it's better to do it before you get there.
Okay. Yeah. I know we also use lock wire as well, typically on all of our threaded components. We use that as well, but yes, a hard wire, a hard physical lock would be good as well.
Okay.
Okay, so that was these were kind of laid out and earlier as well. But with we run our fin flutter calcs. We do hand calcs, and then we also do them in Excel. And then so we ran our fin flutter calcs here. They were not being cut off before, but they are now. But we're getting a sustainer fin flutter boundary of like 6383 feet per second, and then a booster fin flutter boundary of about approximately 4,000, like 3957. We have a stability margin for our sustainer of 2.3, and we have a total rocket stability margin of around 4.8. And then we also have our centers of gravity and centers of pressure. Our center of gravity for the sustainer is 72.28 inches. Center of pressure is 82. And then our rail exit velocity is going to be 128 feet per second.
And that's based on your 30-foot rate.
Sorry, can you repeat that? You lagged a little bit.
Okay, the rail exit velocity, you're basing that off your rail, right?
Yes, our 30-foot rail.
Okay.
Yep.
Yeah, the only number that concerns me a little bit on that list is the 4.9 on the stack is a little bit high, particularly since it's a 6-inch booster. I mean, that's kind of getting up there where you start worrying about weather cocking and that sort of thing coming off the rail. After I encouraged you to increase the fin height, I wouldn't want to tell you to go back on that, but but you could, if you, I sometimes, once I'm really sure what the rocket characteristics and weights are going to be, I have been known to trim a ½ inch off the fin tips, just to get exactly the stability that I want.
Okay. I know we typically shoot for all of our rockets 2 stages. We shoot for around 4. But yeah, I know with our fins, they were a little small. So that's part of the reason our stability is higher there. I know we talked about it, and that's why the semi span of our fins is 6 inches now. But that brought it from like a 4.1, 4.2 inch, or 4.1, 4.2 cow stability to like 4.8, 4.9. Bumping them out from, I think they were at 5, 5.5.
Yeah, I think originally the last version I saw, they were 4. And that's not what you want either.
Yeah.
But I mean, six is good. We just need to be a little bit careful on the wind at launch, which is probably a good segue for me just to mention that there's going to be a great deal of attention this year on the wind velocity at launch. I'm not sure. Were you guys at the event last year? Or you did a single stage last year, right?
Yeah, we had a single stage.
Okay, were you there?
Yes.
Oh, okay, so you know that rockets were being flown when the wind velocity was pretty high.
Yeah, we were about the cutoff last year. I remember we were just under the cutoff for those conditions that we had.
Yeah, and Esra got into a little bit of hot water for launching in the conditions that many of the rockets went. It was sort of a rock and a hard place for him, because if they hadn't continued to launch, there would have been teams that didn't fly, and they wanted everyone to fly. But this year there was some concern from the Spaceport folks about launching in those conditions, and so there's going to be a great deal of visibility on not flying when the wind is high, particularly the 2-stage flights. So just fair warning that the time that people have to be able to fly may be reduced over what it was last year if the wind conditions are the same. And so I'm encouraging all of the teams to do everything they can to fly as early in the morning as possible.
Okay.
And it's my understanding that they may allow a few members of the 2-stage teams and maybe the hybrid teams to stay overnight at Spaceport, so that you can sort of hit the ground running the next day. Now, I don't have confirmation on that, but one of the problems that they've had from time to time there is just being able to get into the facility early in the morning. There's a traffic jam and other stuff going on there. And I hope some of that gets fixed. But my message is organize your schedule and organize your team and organize your tasks so that you can launch as early in the morning as possible.
Okay.
I will say, a couple of years ago, Akron launched the 2-stage, and they probably came as close to being able to launch early in the morning as any team ever has. But even they were, probably 10 or 11 o'clock by the time they finally got going. I mean, we need to have 2-stage rockets on the pad ready to fly by 8 in the morning.
Okay.
And so, even if you fly the next day instead of that, that afternoon, but you can launch early. That's the strategy that you should employ, because we're just not going to launch 2-stage rockets in a 20-mile-an-hour wind. Just not going to happen. So if you want to ensure that you're able to fly, you want to be able to fly as early as possible.
Okay. Did they have, I know you said it was still, like they were still kind of figuring it out. Is there an average wind speed that we should be looking at as we're looking at the weather report? And like 10 miles an hour, or is there a certain one that they've said yet by chance? Or
well, I mean, they're going to follow the AAA safety code and not launch above 20 miles an hour. I'm kind of inclined from the point of view of the 2 stages to maybe set that at not more than 15. And it'll depend on the rocket too. I mean, you have a 30-foot rail, so that gives you, some advantage over teams that are flying big rockets off a 17-foot rail. So, it'll be rocket specific. But, if there's a concern about having a rocket go uncontrolled because of the wind velocities, then we're not going to fly it. We're going to wait until the next morning. And people are going to have to get there early enough and prepared well enough to be able to fly before the wind starts coming up. Because we just can't afford to do what we did last year. We had 2-stage rockets flying over the crowd, and they didn't even light. So, they weathercocked so severely. So we're just not going to do that this year.
Okay. Well, that's good to keep in mind. I appreciate it. So yeah, I guess we can get a little bit into like individual components. We're gonna start with our structures. So that is our entire airframe. Like I said, the X-Winder project just unfortunately was not meeting our timelines for what we wanted to do for this competition. So we weren't able to X-wind all of our body tubes. So we ended up just going with COTS body tubes, buying COTS body tubes again off Mad Cow. Our booster has an ID of 6, and then our sustainer has an ID of 3.85. We're gonna have our bulkheads are all 6061. They are attached to our airframe via 6 ¼ 20 screws, and then in between they are sandwiching our avionics bays. So they're going to hold all of our hardware for our Raptor charges, for our eye bolts, and then terminal blocks as well. So everything that we're using for parachute ejection is going to be housed on those bulkheads in both stages.
Let me make sure I understand one thing, because I'm not sure exactly what I'm looking at here. Can you tell me that all of the couplers that you're using will have at least a 1 caliber overlap?
Yes, they will.
Yeah, because 2 years ago, the team had those bulkheads that fastened together that were glued onto the airframe, and so I just want to make sure that you're not doing that, but you're doing the conventional coupler tubes.
Yes, our 6-inch airframe, all of our couplers are 1 foot long, and then for our 4-inch airframe, each of the couplers are at least 8. I think one of them is sitting at 10. So
okay.
Yeah. Okay, we'll do that. So the new piece of hardware that we're bringing one of the new pieces of hardware that we're bringing this year, it's not new to the team, but it's new to Spaceport, is our transition module. It's how we're transitioning from our 6-inch to our 4-inch. It's 6061 aluminum, attaching to our 6-inch airframe via 2 rows of 6 ¼ 20 screws. And then actually inside we have a flat base that was milled down to, that we're going to be mounting our charge cups and having wire pass-through holes into for our stage separation, our black powder charges. Our payload is also going to be housed inside of our transition module. Not completely. It's going to be housed halfway, around halfway. So we'll get into that more later, but the bulkhead that the payload will be sitting on is that thick bulkhead in the bottom right of the screen. It's also going to be mounted to the airframe using 6 ¼ 20 screws, but that might be increasing to 8 or 10, or 2 rows of 6. We've been talking about increasing that as well, so we have more retention of the body tube. And then we'll also have shims inside of our transition module that are going to keep our payload from moving around inside the transition module, and those are going to be printed out of ABS, and those will be screwed into the transition module walls.
I'm a little confused about this piece. I thought that the transition coupler was going to come off to release the payload. So why are there screws holding the airframe on?
It will come off. That will be after flight. So it's going to be attached to the airframe throughout flight, and then we're gonna take the transition module off for the payload to come out.
Including all the screws?
Yes, yeah, we're going to take all the screws out and just pop the entire transition module piece off. Once the booster's landed, we just plan on walking up and taking the transition module off.
Okay.
So that'll entail unscrewing all 12 of those, and then with that, once we pull it off, the payload will be partially suspended outside of the body tube. So, do you have any more questions on this piece?
No. Well, I will ask one question. Now, this is all out of aluminum, right? And so your interstate's coupler is going to be the bottom of your sustainer motor, right?
Yes.
And is there a sleeve around the bottom of the sustainer motor? I thought I saw that in the file.
Yes, there will be. We have a friction fit, basically, aluminum sleeve that will slide over top of our blue casing, our motor casing for our sustainer. And it's going to sit flush with the top of the transition module, and it's going to have the same fin tabs as well. So the fins are going to slot into that, and then also slot into the transition module. So there's no rotation that's occurring during flight.
Okay. As long as I'm looking at this picture, so you're going to bring wires down from above around your sustainer motor?
For our charge cups?
Yes.
No, we're going to be wiring those up from the booster avionics bay.
Okay. I don't think that's what your wiring diagram shows. Assuming that's the case, you probably ought to update the wiring diagram to show what that's doing.
Okay. We'll take a look.
I don't know if we're going to show the wiring diagram. We can look at that, but I know the one that I looked at a bit ago had the motor ignition and the separation charge from the same Easy Mega in the sustainer.
So we have an easy timer that we will be that will be in our booster bay, and that's what we're going to be controlling most of our stage separation with.
Okay, same comment. It needs to be on the wiring diagram if you're going to do it that way.
Okay, we'll update that. Yeah, because I'm not.
I don't know if I'm doing the review at Spaceport or not. It may be somebody else, and in which case you guys show the drawings that are what you're actually going to do.
Okay. Make sure to update that as well. Cool. Okay. Oh, this isn't working. Okay.
Turn up the volume on this a little bit. It's very quiet.
So another part of the next part of our structures that we have is our fin retention and our fins. We flew this last year, but we're going to be flying this on our sustainer. So
this one, I think.
The big change with our fin retention this year is that we were on a big weight reduction mission as a team because we're flying another rocket. Actually, we're leaving at the end of the week to go to fly another rocket. And we've been trying to weight reduce as much as possible. So that's what you see below. You see an isogrid pattern on our fin retention now. That reduced the weight of each piece by about a third, which was pretty significant for us, what we were trying to do. But these are also made out of 6061. These are 661 aluminum. They fit with our sustainer fins at a full 12-inch root cord, and then we have a ID on the fin retention of 3.865. They're fastened together through the fins by 7 1/4-20 countersunk screws. And then you can see our general fin geometries up there. So we have a semi-span of 4 inches for our sustainer, a tip cord of 5.5 inches, a root cord of 12 inches, and then a 3/16 thickness. And those will also be 6061. So.
Okay.
So that was the sustainer fin can. We have the booster fin can now, but that's going to be our composite layup, which is our tip-to-tip layup. So we found this to be even more of a lightweight kind of alternative to our aluminum fin can. That's something we've been testing over the past 2 years. Like I said earlier, we finally flew it on our liquid engine rocket that flew a couple months ago, and it was a successful flight, better than we could have anticipated. So it was really, really great. That process, we're using CE 306 fiberglass base pre-preg sheets that we were given from Collins Aerospace. The way we're doing the layup is a 0, 30, 60, 90 degree orientation. We're doing 4 layers of it. As you can see in the picture, you can see how the way that in which we're orienting the sheets, they end up at different lengths across our fins. So they slowly build their way out across the body tube and across the fins until they eventually lap over top of the edge of the fin. So we used our pre-preg, and then we also have a peel ply that we use for leaving a nice finish on our rocket. On top of that, we have our release film, which we're using an R120 P3 perforated, which kind of gives a barrier between the actual layup itself and then the breather and the vacuum bag. And then with that, we have our breather layer, which allows us to kind of evenly distribute pressure throughout the entire layup while it's under vacuum, because we do send our layups we were sending our layups to Collins, and we were using their autoclave. So we go through our autoclave to go through the entire cure process, speed up the cure process. That's what I mentioned earlier, where we were looking at some different people that had autoclaves because Collins was having issues with theirs. That's why we don't have our layup here at the moment. But we've done multiple of them before, and we plan to do the exact same process.
What temperature do they use for that?
They have a ramp up process, so it gets to a max of 250 degrees Fahrenheit, or it's 121 degrees Celsius. So they get up to that max for about an hour and a half.
Okay. And you said this was a through the wall fin?
Yes, it is.
And looking at the picture, how long is the slot relative to the fin root? Is it all the way?
So on the no, it is not all the way. On our Spaceport fins, we have a 16-inch root cord, and we're doing an 8-inch long tab.
Okay. Yeah, that kind of makes sense. I'm going to resist standing on my soapbox, except I can't resist. One of the things that always kind of bothers me, I guess, about the through the wall approach is well, using it in the first place with fiberglass tubes. because you buy this fiberglass tube and then you put a big slot in it and lose the strength of it.
Mhm.
So only having the slot being half of the root is a good idea. The other general comment I'll offer is that since you're not minimum diameter on the booster, one of the things that helps keep fins on is keeping that tube round at that point. So one thing people would do is they would, have a centering ring before and after those fin tabs, for example, because those centering rings help keep the tube round, and that's how you keep fins attached. Once the tube starts deforming, then then it's easy, even when you have the tip on there, for the layup to fail. So keeping the tube round is important. You still need to have fillets or something on the inside of the airframe up against the motor tube.
Yeah. We use a like a Bondo fiberglass epoxy resin filler, and that kind of helps us fill any of the gaps that we have in our like adhesion between the fin and the body tube itself. When we send to the autoclave, we actually do have two centering rings that we put on either side as well. And then with the actual motor casing itself, we'll have two as well. So I know that's something we were looking at because we saw some when we were researching it. We saw it in the past, so that works out really well actually.
Okay.
Which I guess we can kind of see here. For our motor retention, we have those 3 concentric motor rings. They're each going to be an inch thick, and then they're each going to be mounted to the airframe via 8 1/4-20 screws. You can see we're going to have one that sits at the base. That's where we're going to be mounting our aeropack to for our COTS motor. And then we're going to have one right above the fins. And then we're going to have one at almost the very top of the motor casing itself. So we're going to have 3 in there along our body tube. For our sustainer, we're a little bit different because it is a minimum diameter. We're going to be mounting to a top plate on our spacer assembly that goes into our motor casing, which will be detailed a lot more later in the solids propulsion slides. But yeah, we'll be attaching via that top plate, which will be attached to our forward closure in our motor casing.
Okay, and where are the 8 out of the 16-inch slots going to go on those fins?
In terms of the root cord itself, they're going to be directly in the middle. So we're going to have 4 on either side of 4 inches of root cord on either side of the tab. If that's what you're asking.
Okay, so there's not really centering rings up against the tabs.
Not directly against the tabs, but right above the root cord itself, and then right below the root cord itself.
And is there a motor tube, or are you just sliding in the case into centering rings? I guess
No,
if you're
there's no
using a
motor tube.
retainer, there must be a motor tube.
We're going to have the motor casing itself sliding up in there.
Okay, so you're not using a motor tube.
No.
A motor tube is around the motor.
No, we are not using a motor tube.
Okay. So okay, I don't want to beat this to death, but I don't understand yet. You have tabs coming through. What are those tabs attached to if there's no motor tube?
The tabs coming through the fins, or on the fins.
Yes.
We're going to be filleting them to the inside of the body tube themselves. That's how we've done it in the past.
Okay, so the inside of the 6-inch body tube.
Yes.
Okay.
Is the diagram on the right of the sustainer or the booster?
That is the diagram on the right is the booster.
Ah, okay.
Okay. And you have not built this yet, is that correct?
The layup has not been built yet. Yes.
Okay. Well, it's sort of hard to tell just based on looking at this at the moment, but I think if it were me, I'd add a couple centering rings in there, above and below each of the tabs, because you basically have a 2 foot long, 6-inch body tube that's not supported. And all of your fin deformation is going to be on that tube, that 6-inch tube that's not supported.
Mm-hmm.
If it were me, I'd add a couple centering rings above and below those tabs to stiffen that section.
Okay. I know we've had issues. We didn't want to drill through our layup. So that's the reason that the centering rings are right above and right below, so that we're not going through the layup. Do you have any suggestions for how you would mount those?
Yeah. Well, again, I'm not 100% sure what I'm looking at. But would there be some reason? I mean, if you've got a 2-foot section of tube, and that's the spacing between the centering rings, but you've got an 8-inch tab in the center of that, is there some reason that you wouldn't be able to slide a centering ring 8 inches up into the bottom of the tube and 8 inches down, so that you've got a centering ring on either side of the tab?
It's possible. I'm not sure exactly how to secure them. Off the top of my head, I wouldn't be sure how to secure those without having them rattling around.
Well, I would. Why wouldn't you just fillet them to the 6-inch body tube?
Sorry, can you repeat that? I apologize.
Well, I mean, if you slid in a centering ring above and below the tabs, why wouldn't you just glue them to the 6-inch body tube?
We could glue them. Yeah, we could. That is a possibility. We could glue them. I was thinking about like physically mounting them with screws, but glue is a possibility.
Yeah, I mean, I'll just let you do what you want to do there, but I'll just tell you that a 6-inch Wildman style body tube is not going to be very rigid if you've cut slots in it and it's not supported by centering rings. So you can dramatically increase the strength of the fin can by putting strategically located centering rings above and below each of those fin tabs.
Okay. We'll definitely look into that then.
Yeah, just take a look at it, see if it looks like it makes sense. But my guess is that you would be able to move the fins around. Now, it is a booster. It's not going to go, exceptionally fast. But that's my 2 cents.
Okay. No, thank you. Appreciate it.
Hey, Harry, how's it going?
Oh, pretty good. I, for some reason, was thinking this started at 6.
Well, you'll have to watch the video.
Yeah. Well, I'm kind of back up anyway.
Okay, we can go on.
Okay. Yeah, so next was our avionics bay. So I'm going to detail a little bit of the physical design of it, and then I'm going to actually pass it off to one of our avionics members to explain our sensor systems and our recovery systems. But our booster bay is a 6-inch OD to fit the body tube. It's a 12-inch length from the outside of the face, like the top of the face to the bottom of the opposite bulkhead, if that makes sense. We're going to be using 2 strata-loggers in the booster bay and 1 featherweight GPS and then 1 easy timer. And then similar to talking about the bulkheads earlier, we're going to have 2 Raptor charges with CO2 canisters on each side. And then we're going to have 4 terminal blocks as well. And then we're going to have an eye bolt on the top and an eye bolt on the bottom for recovery hardware. Our sustainer bay, conversely, is going to be 3.85-inch OD, so to fit in our 4-inch body tubes, with a 14-inch outer face to outer face length. Our bay hardware, we're going to have 1 Easy Mega in there, 1 Stratologger, and then 1 Big Red B GPS. And then our recovery has similar hardware as we had on the booster, but we're going to have 2 eye bolts on each bulkhead in the sustainer, mainly because of the sizing and the placement of holes that we could have on those bulkheads. So we couldn't put 1 eye bolt directly in the center because of our Raptor charges and the size of the bulkhead itself. So can you pass me that 4-inch bulkhead? So we're going to have 2 eye bolts like this, and then our Raptor charges on 90 degrees blocked from one another. So I can show this more if you guys would like to see it. But that's kind of what the general build of the bay is going to have. We also have 6 key switches on each of those bays.
And it kind of looks like that once you install the CO2, that those eye bolts won't be able to unscrew. Would that be likely?
Yes. Yeah. They normally, we can only twist them. We can twist them down to a certain point, and then they lock in with the Raptor charges.
Okay.
So with that, I'm actually going to have our avionics lead. His name is Van. He's going to be talking about the sensor systems. So I'll let him talk to you guys a little bit. You're going to have to click because the arrow keys aren't working for some reason. So.
Hello. We've been developing a SRAD data collection computer for about 3 years now. It's called Chroma. We're going to be flying the 3rd iteration of it on Project Eric at Spaceport this year. Chroma has an array of sensors, 2 IMUs, which we use to collect linear and angular acceleration values. And then we have 2 barometers on it that derive altitude from that, and then a GPS and a magnetometer. All this information is going to be relayed over to our ground station via RFD system, 900 megahertz band, classic polarized antennas. The entire system is going to be powered by another SRAD component that we have, which shifts down a 12-volt input to a 3-volt output for all of our logic systems.
Okay, and you have in fact switched from LiPo to lithium ion for that?
Yes, we will have 3 lithium ion batteries in series using a off-the-shelf coupler, and then that'll be providing the power to our voltage regulator, and that will provide a stable 5-volt output for all of our avionics components that require 5 volts.
Okay.
And then for our recovery system, I think Eric mentioned most of it. Our booster bay is going to have 2 Stratologgers, which are in charge of setting off our main and drogue parachutes. They kind of act as redundant systems. If one of them fails, the other one should hopefully set off our parachutes. We'll have 1 featherweight GPS to relocate the rocket once it's landed, and an easy timer to set off the black powder charges for stage separation. And then in the sustainer bay, we'll have an easy mega to ignite the 2nd stage and also set off parachutes, and that's paired up with another Stratologger as a redundant backup, and then that stage will have a Big Red B GPS interfacing with our custom hardware on the ground, and that's how we'll recover it from there.
Okay, the booster stratologgers, so the wiring diagram showed 9-volt batteries for those.
Yes.
Okay, the easy timer, is that going to be I mean, is that going to be the stage separation timer?
Yes.
Then, that easy timer.
Yes.
Okay, and what's powering that? Do you have a small LiPo for that?
That will also be on a 9-volt battery. Those are.
Okay, they can use 9 volts. Okay.
Yeah.
Okay, so then you're going to have an easy mega, and how are you powering that?
Those ship with a 1-cell LiPo, as far as I remember, and that's how we'll be powering that.
Okay, and what about the stratologger? Because the wiring diagram was showing a LiPo for that.
No, all of our stratologgers should be 9-volt batteries. Might have been a
Okay,
copy and
make
paste
sure
error.
that the wiring diagram is updated, because on the one from the second report, it was showing a LiPo for that.
Okay, we'll do.
And under the description for Easy Mega, it says stage separation computer. Is that not correct?
The Easy Megas are capable of doing stage separation. They have 6 pyro channels, but because of the restrictions of the 4-inch body tube, we don't have any space to run the wire down to the separation charges. So we won't be using it as a stage separation computer. We'll just be using it as an ignition computer for the second stage.
All right. And are you going to be doing the programming for the altimeters?
Yes.
Okay, I sent out some information on how an Easy Mega would be used for motor ignition. Did you receive that?
Regarding the tilt lock.
Well, that was certainly part of it, but
Okay.
it was about a 1-page description of how it is that you go about determining what an altitude check is. And if you have not seen it, then, I mean, hopefully you received it.
I believe we have received it. I haven't seen it yet, but I'll check with our chief E and go over that with him.
Okay, yeah, if you didn't receive that from me, then let me know and I'll resend it.
Will do.
I get fairly prescriptive about the Easy Mega program because we don't want to have sustainers lighting incorrectly. So I'll either want you to pretty much do it exactly as it's laid out there, and to be able to describe how it is, you know, fitting into that format. How did you select the altitude check altitude and the variables that go with it? If you want to do something different, you can, but you're going to have to fight me about it and prove that what you're doing is safe.
Will do.
So you can do that if you want, but I just don't recommend it. But be able to describe, you know, in the context of that write-up, how you did the programming, so that we'll be on the same page. Okay. On the easy timer, it confuses me in the information provided. Are you separating before you're lighting the sustainer motor, or only separating if it doesn't separate on its own?
So we're separating before lighting the sustainer motor.
Okay.
The easy timer will determine when our acceleration is changing to a point where the booster motor is done burning, and then there is a timing sequence after that. I believe it's 5 seconds right now, based on our previous information, but I can double check that. 5 seconds after the booster stops burning, it will set off the ejection charges for stage separation. And then from there, the Easy Mega will handle the second stage ignition.
Okay. And you said you were planning to separate the booster stage after how much time?
5 seconds after the acceleration change is detected.
Okay, 5 seconds after burnout.
Yes.
Okay. I would recommend that you look at the stability of the rocket during that coast period. And if you're at 4+ on the pad, you may be at 9 or something during that coast period.
Mhm.
In which case you might want to strongly consider separating the booster earlier. Because if you leave it on there and it doesn't drag separate on its own, and I wouldn't assume that it will, then you're susceptible to any crosswinds, with a very high stability like that. So we should probably look at it in your simulation, but that's I've seen that, and you probably don't really want to do that if that's the case you find yourself in. Okay, so as far as lighting the sustainer motor, now you didn't show on the wiring diagram a switch to that igniter. Will you have one?
A switch to the igniter itself, or a switch to the Easy Mega?
There, in the rules, it is a requirement that there is a switch that disconnects the igniter from the altimeter. So in other words, you're going to have a wire that goes to your head end igniter, and from your altimeter, there has to be a switch in that line.
Well, we will add that in there. We have a redundant key switch on our sustainer avionics space, so we'll just fit that to
This is not switching the battery. This is actually
Mhm.
switching the minimum requirement is to disconnect one of the leads.
Understood.
An improvement over that is to use a double throw and disconnect both. A further improvement to that is to use a disconnect that disconnects, but then shunts the head end igniter when it's in the off position. So it's a double pull, double throw, and many teams that are doing two-stage are using double pull, double throw that shunts in the off position. Okay.
Mhm.
So the switch is a rule. The upgrades are optional, but I'll tell you what, if I'm using a head end igniter, I'm going to shunt that motor igniter.
Understood. We'll try and see if we can fit it into our bay.
Well, you have to. You don't have a choice.
Wait, the shunting the igniter is mandatory?
No, you have to have a switch.
Okay.
But a key switch that provided that function, you can as easily have a key switch that provides a shunt as one that doesn't. It's just a matter of maybe ordering a different key switch, but it's the same form factor. Okay, that's it on this slide.
All right, I'll hand it over to Eric again.
Okay. So next part is our recovery systems. So kind of going off of recovery, the actual parachutes themselves. So we're doing a dual deployment system for both of our stages. Our drogues are both going to be deploying at apogee, and our mains, as of now, are both deploying at 1,000 feet for both of the stages. We use a hemispherical geometry for our drogues and a toroidal for both of our mains. And they are all going to be made out of ripstop nylon. So you can kind of see how they're attached in the diagrams. But
Can you run through that diagram real quick, because it's too small and I can't really see what it says.
Yeah, so
here we actually have a recovery lead here as well that we'll be talking as well. So
hi. So basically our shroud lines for all of our parachutes, they are split in half, and those get their own individual quick links that we connect to a bridle that has its own swivel. And then those have Kevlar cords with their own individual quick links that'll connect to the eye bolts on our bulkheads.
Okay, so if I started from the bottom of that drawing, that's the two individual connection points to the rocket, right? The upper
Yeah.
airframe and the lower, okay. And then you're going to, yeah, I guess, what's the purpose of the single shroud line coming down from the parachute? Or how long is that?
The bridle cord? Or do you mean the center line coming from the main?
Well, what I see is the parachute comes down and I see the two quick links.
Mhm.
And then I see a swivel. And then I see what looks to be a length of harness that goes down to another quick link.
Yes, we use bridles that are about 3 feet in length. That's just what we attach our swivel links to.
Okay. Are you going to be able to show this to us a little bit later? I want to make sure I understand what this is.
Yeah, I can show you how we assemble our quick links.
Okay. Yeah. One reason, and I'll, I get on my soapbox again. Hardware is one of its functions is to attach things together. Another one of its functions is to tangle things up.
Mhm.
My when I do a level 3 certification, one thing I tell people is less hardware is better.
Yeah, that makes sense.
And it looks like you've got a lot of hardware on the chutes.
Yeah,
So
a little bit.
yeah, so there's no rule against doing that. I would just offer that hardware is a place for lines to tangle, and I always try to minimize it to the extent possible. I would say, for example, on a parachute, or on a main parachute, I'm not sure you need a swivel. It's only going to be flying for a short amount of time. Do you really need one? Maybe not. Drogues, sure, you should have a swivel on a drogue. Anyway, I'll get off my soapbox now. But
You're good.
some thoughts on things that tend to make certification flights successful or not.
Okay. Well, yeah, we'll definitely, we can show you that.
Okay.
So that was our parachutes themselves. Our ejection system, we use a CO2 pyro piston design, for all of our ejection systems in both the main and drogue, parachute releases. You can kind of see the breakdown of an individual system there, including the canister themselves. So, it starts by, we have a little black powder charge up on the top that energizes once it's activated by the stratologger. It energizes the spring piston, and then that piston actually punctures our CO2 canister. And then you can see the holes in part of the Raptor assembly itself, that will allow CO2 to fill up the rest of our bay. So we've been flying this for a bunch of rockets now, and they've all been very successful. We actually just had an ejection test for our rocket last week, for one of our rockets last week, and we ran 8 successful ejection CO2 charges. So that's what we use for our base separation.
And you're just going to use one E-match in each one?
Yes.
Okay, and obviously one CO2 is enough to separate.
We have a primary and a redundancy on each bay. So the redundancy is typically sized at like 1 1/4, but we can only buy the size the manufacturer has, so we most of the time go bigger.
Okay.
And then lastly is our stage separation. I know it was talked about. I know Van talked about it earlier as well. It's a redundancy. Ideally, we do drag separate, and that is our first form of stage separation. But if drag separating doesn't occur because of a way in which we're cocked, we do have 2 black powder charges that are housed inside the transition module. Van explained how they were set off via the easy timer, but we have 1 black powder charge that acts as a primary, but that primary is actually our redundancy. And then we have a second black powder charge that is like our secondary redundancy in the transition module themselves. So that's how our stage separation occurs.
Okay, and you're gonna run those both off the same easy timer.
Yes.
And how much black powder are in those separation charges?
Around probably what, 5 grams? Around 5 to 7 grams.
Wow,
No.
that's a lot of powder.
Yeah, if I understand your design correctly, you're gonna have the bottom of the motor, I mean, the open volume of the area where the black powder goes is going to be fairly small, like 4 inches in diameter and maybe an inch long or something.
On the inside of the transition module, yes.
3 grams.
Oh, okay. I apologize. Sorry. That was actually for our other rocket. We do about 2 to 3 grams for this one.
Okay. I would use about a half a gram. And this assumes that the volume of the space that I described is what you actually have. A 4-inch diameter void that's maybe an inch or so long.
Yes. I
In other
know
words,
typically
you
we've
know,
accounted for the core diameter of the motor itself as well, which we have to take into account.
Okay. Well, you can pressurize the core if you want. It's a good idea not to. If you were not pressurizing the core, you might use about a half a gram of black powder.
Okay.
This does not take that much.
Mhm.
If you are pressurizing the core, I wouldn't pressurize the core.
Okay.
Yeah,
Okay.
I mean, you can come up with some sort of a cap over the nozzle or something so that you don't
Mhm.
have to pressurize the core. It's just an unnecessary thing.
Okay. Yeah, we'll look into that as well. I know typically in the past that's just what we've done, but yeah, we'll definitely look to some sort of cap because it is a lot.
Well, I mean, you can do it. There's no rule not to. It's just that, why do you want to expose your grains to a pressure spike?
Yeah.
If you don't have to.
That makes sense. Yeah. Yeah, I understand that.
Yeah, that would be a good thing to ground test. Another thing to do on the separation is to examine your simulations to see how much force you might actually need for that separation, which you can do with like the open rocket and the RAS Aero simulations. You can examine the rocket to see what that separation force would likely need to be.
Okay. Okay. Yeah. I did not. I haven't looked at that. So yeah, I will look at that as well.
Okay.
Yeah. Okay. Well, the next part is our payload system. So I'm gonna pass it off again to one of our payload leads. And one of our payload leads. He'll be talking about the whole project. So this is Henry. All right, hi y'all.
I'm really interested in the payload and what it's going to do, but in the interest of time, I'm going to ask you to kind of limit what you say to deal with the safety aspects of the
Yeah,
payload.
I can keep it quick. I can skip over our mission statement and stuff like that. I know we're trying to
Yeah,
speed through this.
Yeah, that's interesting, but I really just want to, we still have a lot of stuff to cover. So maybe just
Yeah,
give us
let's.
a high level, but
Yeah,
things
I'll
like
give you a quick
oh,
2-minute overview.
okay.
So our payload is 2 parts. We got the launcher, which is a 3U CubeSat, and then Firehawk, which is the plane. The plane will be deployed once it's on the ground. We'll walk up to the rocket, remove the transition module as we talked about, and then autonomously the plane will launch out of the rocket. Low flying, probably 20 to 30 feet up in the air maximum. So we're not worried about anything else like that with GPS and other issues there. None of this should be an issue because it's completely enclosed. So we can skip forward to integration. So for the payload integration, this is pretty much the main part I'll touch on. We're mounting it to the transition module with a 2-inch bulkhead, and then attaching to that bulkhead is that back plate you can see called out there in that picture. Just 4 1032 screws. We'll have nuts on the back. We have drop tested it. Shouldn't be too big of a deal, considering the whole thing is within the transition module during flight. Let's see, what else should I touch on? You can see the picture there. So it will have 3D printed spacers just to keep it safe, keep it from kind of rattling within the bay. But not a lot of integration issues that we should see, considering it's completely within the transition module throughout flight. So are there any questions you guys might have? I know it's not too much.
Yeah, I think the main thing is just not to have it able to move around a lot.
Mhm.
I have to think about it in this particular position in the rock. What would be the implications if it could move? But you want to have it secured so that you don't have stuff flopping around, acting
Right.
like a battering ram or things like
Yeah,
that.
exactly. Yeah, with those spacers, we're not too worried about it, and it's secured at the end. So even without spacers, it shouldn't be moving around unless something were to break. But yeah, it shouldn't be too much of an issue.
Okay, so this is going to have the 6-inch airframe around it, right?
Yeah, that's correct.
And so that airframe then is going to go down over the main chute, and then it's going to get shear pinned down lower, right?
Yes, that's correct. Right?
Yes, it will be.
Okay, so those shear pins are going to see the weight of not only the interstage coupler, but also the payload, right?
Yeah, that's correct.
Okay, so I haven't added those up, but that's going to be a lot of weight, and so one thing that you're going to have to deal with is making sure that you don't put out a main at apogee. Although if apogee is 1,600 feet, it's only a 100-foot drop. So that would not exactly be catastrophic, but yeah, that would be that's sort of a difficult task, having that much weight. If you've got when the drogue charge comes off, that you don't get a main at apogee with the heavy top end like that.
Yeah, for sure.
Yeah, we with the way that the body tubes are resting on one another, we're not, at least through booster flight, we weren't as concerned about that weight because the body tubes are going to be taking most of that force, and not so much because of the way that the coupler is mounted to our avionics bay, which is mounted to a body tube. We weren't as concerned of the shear pins taking most of that force themselves, if that makes sense. So that's where our thought process was.
Well, the concern is always, when the drogue charge goes off and the rocket separates, when it gets to when the drogue catches, there's a big jerk in the airframe, and the weight of the transition coupler and the payload can cause the shear pins to break. If you've got horizontal velocity, you can easily break the shear pins in there when the drogue catches. right?
No, that
Just-
makes sense.
Okay, so the trick is to figure out how to mitigate that jerk so that you don't put out the main at apogee. And the kind of things you do, or you use a nice long shot cord so that the top section can slow down before the drogue catches. You can use a smaller drogue if it's appropriate, so there isn't as much force. And you can use more shear pins. How many do you plan to use?
We typically use 4 on each of our separation points.
Okay. Like number 4 shear pins?
Oh no, 4 shear pins. I'm not exactly sure on the. I'll have to look at the thread size. I'm not exactly sure the size, the thread size of them. But they're comparable to 632s.
Okay, that would be a number 6 shear pin then. If it, okay.
Mhm.
Okay, I've never used a number 6 shear pin. Those frighten me. You know, if you ground test them, it's fine.
Mhm.
You know, I might use in a situation like that, maybe 8 number 4s. But if you want to use number 6s, that's fine too. Just, you know, you with the design you have, and the weight that you're going to have there, you want to have lots of shear pin grab at that point.
Mhm. No, that makes sense.
Okay,
Great. Thank you guys.
What was that?
Yeah, this should be understood.
Okay.
take a video when it comes out.
We will.
Yeah, we will for sure.
Mhm. So for propulsion, it's going to be passed off to our propulsion manager. His name's Corbin. So he's going to be talking about our SRAD, and then we're going to have our upcoming manager, Logan, talking about our CODs. So those will be the last 2 sections that we have on our presentation today.
Yeah, for sure. So we're going to be flying a motor that we've used quite frequently since about 2020 when we developed Angry Listerine. That's going to be our like typical SRAD blue casing that we've been using. It's worked in the past 4 rockets that it's been in, except for a minor hiccup. Like the motor didn't malfunction, I promise. But we had a minor hiccup of, you know, when I Promise's recovery failed, and we had to change a little bit about the end of it, just refurbish the casing, and we've flown it since then, and it's worked fine. In the configuration right now that it's in, it's pretty much exactly the same as we've flown it about a year ago, end of 2022. Around end of 2022, using the same head and ignition setup and everything like that, just a little bit shorter of propellant length, similar pressure, similar everything else, you know, be about just the same retention method and everything. As far as like details on the head and ignition, I know there were a lot of questions throughout the past couple months of like how the head and ignition works. That's pretty much just a normal starter grain within the head and ignition module that has a hole down the center of it. It's epoxied in. We just have tape there to be safe. And then there's an aluminum screw with a hole down the center of it that screws through the forward closure that has an E-match epoxied into it, of which is then visible inside of the starter grain inside the motor.
Now, the picture on the left is showing 2 E-matches. Or are you using one, I think?
Oh, we're using 1 E-match. There's just, we have a couple of like extra on standby.
Oh, okay, I see. The picture's pretty small.
Yeah.
Okay,
Yeah, it's just 2 bolts next to each other. We just bring extras with us in case that like one of them's faulty.
okay. When do you insert that igniter?
We're going to insert that
Process.
igniter
Go ahead.
just like whenever its final assembly is completed, that igniter will be inserted. And then I believe it's supposed to be shunted when while it's on the launch pad until we arm the key switches.
Okay. Yeah, I mean, the correct answer to that question is we'll put in the igniter when we're at the pad.
Yeah.
And not before that.
Well, right. Yeah. Sorry. I should have specified that. That's my bad.
That's okay. I mean, the reason that I mention it is that on the two-stage pads, you have maybe a little bit more time to do that sort of thing than you would up on the single stage pads. You know, where everyone has to run out and load up the rockets and then leave as quickly as possible. At the two-stage pads, you can hang out for a little bit. So you want to plan to insert that igniter out there at that point. And have it so that, you know, you can assemble things fairly quickly thereafter. And yes, I would definitely recommend that you arrange to shunt that when it's not, you know, when the switch is off.
Right.
You know, and the configuration that you want to use is well, if you do it the way I suggested, which is a key switch that shunts and disconnects, the shunt ought to go downstream of the disconnect so that you're actually shunting the igniter. Now, when you do that, then you turn on your altimeter and you're not going to hear continuity.
Yeah.
Okay. So do you envision dealing with any safety issues as a result of that? How are you going to verify continuity, for example? Are you going to do all this on the ladder, so to speak?
That wouldn't be a question for me to answer. That would be more of one of our avionics guys like Van, but I imagine that we would be doing this all on the ladder. Yeah, he's nodding his head. Yes, we would be.
Okay.
Yep.
Alan, Harry, you got any questions on this?
No, I've talked to Chris several times about the motor. I've seen it fly the last several years, so I'm pretty confident in, you know, the motor itself.
Okay.
How are the forward and the rear bulkheads, how are they retained? Where the nozzle end is retained how?
Okay, so both ends are retained by snap rings. It's just a snap ring motor case. The way that the top end, it's kind of hard to imagine. You kind of have to see it go together. I actually have it here, except for the head and ignition module that's currently at Chris's house, Chris and Steve's place right now, just for safekeeping, so it's not on campus with the igniters and things. The top piece that you see there, this top piece, like if we go to the right picture, the one with the eye bolts and all that stuff, that is how we are retaining the motor to the rest of the vehicle. And there are very long screws going down through there. There's a through hole in that plate on the top that go down through to connect into the forward closure there, which pulls it back, that top plate, onto the motor casing and pulls that forward closure into the spacer, which is then pulled into the snap ring that is at the top of the motor case there. It's the same way that we've retained it during our last launch, just with a little bit longer of a spacer there. The reason the spacer has to be there for this time around is because we were originally back in January planning on using a different motor, but we did testing, like actual static fire testing of that motor. It was going to be a moon burner motor, and that didn't turn out. We didn't feel that it was going to be safe to continue with that project, at least for this launch, and so we returned back to our traditional Bates grain geometry motor. But then we realized it was going to be too powerful, so we had to lower the amount of propellant that we were going to have in the case. And so we could actually stay around that 30,000 foot apogee. And we had already at that time built the rest of our rocket around this motor casing, and so we kind of were forced to design it this way, although we've done it this way before.
But the snap ring retaining the top of the motor is going to be located at the top of the spacer, but the bulkhead containing the head and ignition and the associated sealing O-rings, they're going to go below the spacer.
Yes. Yeah, that's on that module down there.
Got it.
Yep. Yeah, I should say we've also hydrostatic tested this casing this past January to 1,000 psi. It held there for about 10 minutes, 12 minutes, and didn't see any pressure drops or anything like that. And that's the same O-ring configuration and sizing that we're using on the actual flight motor.
Okay, I guess that's it for this. I hadn't realized
sure.
that you were taking grains out and modifying it that way. That's interesting.
Yeah, for sure. Is there any other questions? If there's not, I guess we can go ahead and move on to the booster.
Okay.
Yep. So here's the booster. This is Logan Dillner, our new this upcoming year. He's going to be our new propulsion systems manager. So he's going to talk about our booster motor.
Yeah, so as mentioned earlier, the booster is going to be a COTS motor. So you can see our simulation here on this graph here. Just total impulse is going to be the 21,145 Newton seconds. We're expecting burn time to be about 3.49 seconds and a max thrust of about 8,034.6 Newtons. And then that's the same way as our sustainer. It's the motor is going to be clamped in by the snap rings, and we have an aero pack holding the nozzle in, correct?
Well, the nozzle's held in by a actual retention ring that comes
Yeah.
with the motor casing. It's just a normal COTS motor case. We're getting the reload for it from Harry Spears. The aero pack is what holds the motor into the rest of the cockpit.
Okay.
Yeah, given this particular motor, if I were setting this up and using an easy timer, I would base the easy timer times based on time from liftoff and not time from burnout.
Okay.
Just because you get, this motor always burns 3.5 seconds. And so you can set a time from launch of like 4 seconds or 4.5 seconds if you wanted to reduce it to that, and be fairly confident that the motor was burned out by the time you get there. When you use time from burnout, you're subject to the motor vendor's interpretation of what burnout means. And further, burnout doesn't always mean the motor isn't burning anymore. It simply means the acceleration has reached a certain point for a certain amount of time. It's very common for motor burnout to be detected some period of time, up to as much as 2 seconds after burnout is declared. So, if you're using a COTS motor that's very well characterized like this one, you're probably safer to control the flight to do it from launch and not burn out. Just my experience.
Okay. Yeah, we'll definitely look into that.
Yeah.
Have you assembled an N5800 before?
Yeah, we have. We've assembled it for, I think we used the same motor for the I Promise rocket, and we actually have done it a lot on other rockets and other two-stage rockets we've attempted in the past. I think we have a total of 4 N5800 cases just sitting around. So
okay, I just warn people that are using N5800s that it's a difficult motor to assemble.
Yeah.
And reasons for that are one end of the liner is capped. You can't use the threaded closure to pull the nozzle in. You have to, do it differently. And so if you're not familiar with the things I just said, then you might make sure that you understand how it's going to go together.
Okay.
Because lots of N5800 motors are lost in the construction, trying to glue the grains in and they get locked in, or trying to put the nozzle in and then you shear the O-ring around the nozzle. So
yeah,
it's a difficult motor. So if you've done it, you know that.
Gentlemen, I'm going to have to leave the discussion because I'm using my wife's computer and it is going dead on me and we need to get it recharged. And I have another Zoom meeting at 8 o'clock Eastern. So I'm going to leave you guys now and head on and try to get this computer charged up. Anything else you need from me before I go?
I think we got through the motor part. So I think we're good. Thank you much.
Okay,
Thank you, Alan. It was a pleasure.
Thank you.
sure.
And so we were talking about the fitting at the top of the motor to, for the harness connection.
Yeah.
Okay, I don't know if it's the same as what's shown in that picture there, maybe not, but let's make sure to visit that or revisit that. So one more slide.
I think after this slide, it is just questions. So
Got
I
it,
think
okay.
there's everything else. Yeah, sure.
So if you guys have questions, we can walk you through some of the components that we have. In person here, I can switch to my phone and we can talk. But if you have any questions about anything we've gone over, obviously feel free to bring them up as well. Whatever you guys want to do. We are.
Well, I probably still have some questions I can ask, and then we can go on with the cell phone. A lot of them have been answered though, so I probably just have a couple.
Okay.
What's
Are you having? Do you have 3 or 4 fins?
We have 3 fins.
Okay, because every report changes.
Yeah.
The first, it kind of changed based off of our motors, and initially in our first report and then into our second, we were switching motors back and forth trying to pick a proper motor configuration because of some of the Cesaroni technology vendor issues that we were having initially.
Yeah, initially we weren't able to find a reload until Harry was very kind enough to let us buy one off of him. And so that led us to like try and make some changes because of like launch rail velocity and things like that. But yeah, things are good now.
Okay.
And with that stability, it was the big thing of just flipping back and forth, seeing what stability is what got us close to our 4 cal. But obviously that's a little high, like we talked about before.
Yeah. Well, you know, I'm not going to say that I can with absolute assurance that 4 is too high. I mean, I normally quote a 2 to 3 for a booster on a 2-stage, but I can't say I have a whole lot of data that says that has to be the number. I just look at the flip side of the coin, what it is after burnout, and make sure that it isn't too high at that point, or that you separate the stages quickly. One thing I noticed on the recovery harnesses, there typically was 2 harnesses for the main and 2 for the drogue, and they were almost the same size. So the thing that occurred to me is when it's falling under main or particularly when it's falling under drogue, are the 2 halves of the rocket going to collide together?
No, they're proportioned out based off of the length of the rocket. They're different lengths. It's just in the diagram. We don't have it indicated.
Yeah.
Okay. Yeah, I was just reading the description, and it was like, the one harness is going to be 180 inches, and then the other one's going to be 175, and it's like, well, they're almost identical.
We were, yeah, they will not be identical. I know they are different. Yeah, that diagram just kind of read similar or showed similar
Okay.
sense.
Okay, I don't have any other questions that I identified ahead of time, so maybe we can just take a quick tour.
Okay. Yeah, I need to make sure that I can see. I was having plenty of technical difficulties before. Let me try to switch this real quick.
Yeah, I did one yesterday, and the switching to a different laptop to look at the rocket, that caused a few technical issues then also.
Oh, I hope we don't run into the same. Well, oh, maybe. Is this gonna work? You guys. But I'm muted. Okay. Can you guys hear me now?
Yes.
Okay. So yeah, now we can kind of walk around what we have so far. I'm gonna just take that off the charger, move this over here. So we have some of our physical hardware set up down at the end, and then we can move into our motors initially. Is there anything you guys prefer to look at first, or do you want me to just walk through it?
Well, I'd probably rather see the rocket than your face.
Yeah, obviously. I wouldn't want to see it, so.
There you go.
So yeah, down here we kind of have some of the we have all our body tubes sitting over here. We have this is the layup I was referring to initially. So this is slightly different than what we're using now because these are face adhered versus through tabs. But we did use tabs on our last rocket, but they took it for a tabling event, unfortunately. But this is similar to the layup that we're going to be using on this rocket as well. So, and that will be going on this motor tube.
Okay, and that's done with the same fiberglass prepreg that you're talking about using?
Yes, exactly the same.
Okay. So just out of curiosity, have one of your team members flex on those fins for a minute or two.
Yeah.
They're very hard.
Grab two of them, and not the fin itself, but the can you move the fins, and does the body tube deform?
I'm pressing relatively hard.
Okay, I really can't see one way or another if are they moving at all?
No, they
they're-
flex very minimally.
Yeah, this is very strong.
Yeah, I see very minimal flex.
We get all our materials from Collins Aerospace, which is
Okay.
very strong. Carrying methods and all that stuff.
So yeah, they flex. We found very minimal deformation, and that is even with just a face mount. With our through tabs, it gets a lot better. We've found that it becomes a lot stronger. So.
Okay. All right. Well, I'm that looks pretty good to me. I'm still going to suggest though that the way to keep fins attached is to keep that inner tube from deforming. And the centering rings that I talked about. I'd still take a look at it, but it looks pretty good though.
Okay, thank you. Yeah, we'll definitely take a look at gluing those centering rings in. I appreciate it. So I guess we also have our two avionics bays that we'll be using. We have our booster avionics bay. We 3D print the actual shelves themselves, and then they are attached by threaded rod together to the bulkheads, and we leave slots like you can kind of see in this one for our Raptor charges, for our CO2 canisters with our Raptor charges in them. So this is a similar style how we do it on both ends, 3D printing both of them.
So when is there what is the tube that goes around or between those? What's the bay containment?
We will have a coupler on each end that probably has it has 2 inches of coupler on each side poking into the bay, and then we'll actually have a fiberglass body tube that just contains the whole bay itself on both ends.
Okay, so when I asked the question about the coupler links, that's kind of what I was getting at. I mean, actually, you only have a 2-inch overlap over the altimeter bay.
So we have a 2-inch on each side plus the inch bulkhead, but our separation points are further down. So total down the body tube itself, it's going to be 6 inches of body tube length on our 6-inch coming down, and then 4 inches coming down on our 4-inch. It's not going all the way into the bay, but the body tube extends. Our separation point will be out here, and that's where the 6 inches actually comes from.
Okay.
So.
And as far as unspinning on the booster bay, is that going to be obstructed by the CO2? I'm getting back at the same question. We want to make sure that the harness connection point can't unscrew.
Mm-hmm. No, so it will be the way we attach our eye bolt is it will come through this hole, and we'll actually be able to put a nut as well on the other side. I think Corbin explained earlier how we attach to our forward or our top plate on our motor casing, but we will be able to actually nut the other side of our eye bolt as well as an extra case in there on both ends.
Okay.
If that answers your question.
Yeah, I guess I get more concerned about eye nuts because they can more easily unscrew. If you got the eye bolt, you have the hardware on the other side of the bulkhead.
Mm-hmm. Well, these are what we typically use. These are what we have been using and flying. And they will be locked in on our 4-inch by the Raptor charges as well. So there's not going to be any rotation because they'll be locked in with our Raptor charges here.
Okay, just out of curiosity, how heavy is a section of that aluminum compression case?
Our fin cans?
Yeah.
These are probably about a pound each at most. They're actually probably these are less than a pound.
Okay.
They're with the ISO grid, they're very light components. So they bear almost no weight.
How did you make them? I'm just curious.
On a CNC, we CNC'd to get the ISO grid and the actual pattern, and then we took them to the mill to take off any tabs and then add the screw holes in them and our set screw holes as well.
Okay.
We have a CNC here on campus, so we were able to do it all on campus in our machine shop.
Okay, let's go back to the closure on the N5800. How are we going to keep that from unspinning?
So closure on N5800, are you talking about this one?
Yep.
So we'll typically, we can I know how we mentioned earlier, we'll typically Teflon tape. We can lock wire as well, but that is the way that we hold it in on this typically.
Okay.
We also have Loctite that we can use on demand. We have different levels of it. We haven't specified which one we use on this yet because we haven't tried to bend this with a torque bar yet to see how much force it actually takes to get it undone. But whether we decide to use blue Loctite, would be preferable because we can actually get it undone, or we use red Loctite, it'll just depend on like how much force it actually takes to get this undone. If all else fails and this still doesn't take much force to get undone, we could always just drill a hole through this and through the actual eye bolt itself and pin it. Just temporarily use like a key in there to keep it from spinning.
Yeah, well, I would normally tell people to do that, to put a cotter pin in there. And I would tell them to drill the hole further down, towards the bottom of the stem and not high up on it.
Okay.
But I'll ask Harry for his opinion on that.
Yeah, I mean, if that's something that's preferable, that's.
Yeah, well, I know I've seen several people do the drill through with the cotter pin, and that's not going to come loose.
Okay. Yeah. Yeah. I mean,
yeah,
I don't
I've never used the Loctite myself, and because I like to have something I know can't come apart. I don't know if Loctite is allowed by the rules. Is there any issue on the rules for that, Harry?
Not that I'm aware of. I don't think there are any rules on how the connections are. I can check with Ken on Wednesday.
Well, I haven't seen any, but I mean, if it came to you with Loctite on it, you would be okay with that?
If it looked like it wasn't going to come loose, yeah. But that, generally don't even really see that aspect of it.
Yeah. The question that the concern that I have that I always try to relay to the teams is that you don't necessarily know who your safety reviewer is going to be. And if you run into someone that says Loctite's no good, now you're trying to figure out how to drill a hole on a round cylinder.
Yep.
That sort of thing is a lot easier to do now than it is later. And so that's why I would recommend that you use the cotter pin approach, because that's going to work. Now, you have to be careful doing that, because I had a team a year or so ago that decided that the right way to install a cotter pin was to drill a 1/4 inch hole through there. And they weakened the bolt so much that it just fractured off. So you're not talking about a hole that's very large. I mean, you're talking about almost the smallest drill bit that you can use that would actually be capable of boring a hole in there. So, you don't want to do that either. You get to use, a small cotter pin is all you need, very small.
Okay. I mean, yeah, I see no reason why we shouldn't do that. We have the capability to, so I'd say we're early enough in the game. We'll just go ahead and do that then.
Perfect. Okay. Cool.
Let me. I got one more list of stuff or to ask questions about. Do you have anything else you want to show us real quick?
I guess the last thing, if you wanted to see it, was our actual transition module that we have almost completed our manufacturing on. You can see the plate on the inside that we were talking about, where our Raptor charges are going to be mounted down in there. We have a ring on the outside where our motor casing is actually going to sit. And then on the other side, you can see where our payload is going to be housed in. The shims aren't in there right now, but they will be in there to make like a 4-inch by 4-inch slot for the CubeSat to slide in. So this was our last big component that we had laying out at the moment.
Okay. And I think I had asked that we can maybe take a quick look at the fittings around the parachute connection.
Mhm.
Is that set up to where we can look at that?
Is that possible to look at? Well, if you give us a couple minutes, we'll finish setting it up.
Okay, well, I'll go to my list here real quick. Rail button position. I didn't notice if it was on the new. Nope,
They
it's
were
not on
not.
the open rocket. What do you have in mind for that?
We typically put one. We'll put one on the bottom of the ring, our very bottom ring, at the bottom of the motor casing that has the aero pack on it. And then we'll typically put one on our avionics bay and one up near our transition module. We won't put any on our sustainer because of the difference in diameter, and just creating a lot of drag after the sustainer launches itself. But we typically put 3 to 4 on a rocket like this. So that's where we're planning on putting them.
Okay. Yeah, one suggestion I would offer is on the lower 2 rail buttons,
Mm-hmm.
to have them not all that far apart. On your rocket, maybe 18 to 24 inches might be a reasonable spacing.
Okay.
And then you can have the other button up as high as you can get, and ideally near the CG if you can do that.
Okay.
Now, on a 30-foot rail, I'm not sure it makes a heck of a lot of difference, actually, to be honest. It would make more of a difference if you were launching it off a shorter rail. But that's the spacing that I would recommend.
Okay. Yeah. We typically also try to put one like at the top of our motor casing. So if one of them happens to go, or in that middle ring, if it goes on one of those 2 centering rings as well. But we'll look at the 18 to 24. It gets like we always are basically by that when we're up above the motor casing, but down into the motor casing. We've been a little bit different, at least with our minimum diameters. For this, we can add them lower.
A good idea is to take an extra rail button with you, and of the same style, and then just make sure it fits. Well, it's your pad. You can do that anytime. Never mind. If I had, I've got a gallery of where I take the pictures of the team members sitting on the ground, filing down their rail buttons so they can get them on there. So I tell them to do a test fit ahead of time.
Mm-hmm. No, that makes sense. Yeah, we'll do typically a structures dry run here to make sure they all line up, and then we'll do a full team dry run to make sure that everything is aligned properly after all the components are in. X motor casing, propellant, obviously.
Okay.
What are your rail buttons made out of?
I know I'm blanking on the material at one moment. Delrin, right, Delrin.
Okay. Yeah, know a team that tried to 3D print the rail buttons, and they got it on the rail and they were breaking off.
Yeah, we just buy our rail buttons, and again, we've been always using these same rail buttons since I've been around. Been using the same ones for a long time.
And you've been out to Spaceport, so you know the environment and kind of the nature of it.
Yes.
Yeah. Do you have any questions about what's going to happen?
Not necessarily. I guess the wind was honestly the biggest question I had coming in, and you answered that. because we flew a single stage last year, I guess it's going to be a new environment for some of us. I know we flew a 2-stage a couple years ago, but just kind of just wanted to know what the environment to expect around that. But I guess that was kind of answered as well. So you answered everything I had. I really appreciate it.
Yeah, and Harry, what I told him is we need to try to get them off as early in the morning as we can. And,
Yes.
you know, hopefully
Wind is a major concern this year, and the earlier you can get them up, the better. I've heard talk that we may have to be shutting down at like 2 o'clock every day due to the wind, because of the incidents that happened last year. Spaceport is just really concerned about wind speed, and wind direction.
Mm-hmm.
There's going to be weather stations all over the launch area.
Okay.
Yeah, and so, you know, I just can't emphasize enough the planning process that you should go through to try to figure out what it is you have to do to get out on the pad as early as you can in the morning.
Mm-hmm.
It's just going to be, you know, I don't know how many 2-stage rockets I've launched out there, but it's probably 20 or more, 25, something like that. I don't remember. Every single team has told me, yep, we're going to launch the first day, first thing in the morning. And no team has ever done it. So I mean, literally no team has ever done it. Akron got as close as anyone 2 years ago.
Mm-hmm.
But, you know, no one does what they think they're going to do. And so, you know, all I can do is relay that story and say, you may think you've got it planned, but the idea is to go back over that plan again.
Okay.
And try to figure out, you know, teams always seem to have a problem with something like, well, Bill's got the altimeter base, so we can't start. And, you know, Tom's got the computer and we got to reboot it. I mean, it's stuff like that that kills you on the timing of getting the rocket ready. So, you know, one of the things that I do on 2-stage and 3-stage flights is I have a checklist that is a step-by-step of everything that I'm going to do. And as I'm going through that checklist, I don't think about any of those steps. I just execute them. And I know every single step that I'm going to have to do. And then I know every piece of equipment that I need to have to do that step.
Mm-hmm.
And if you do that, then, you know, every time I launch a big project, it's, you know, it takes me 2 or 3 hours to get it set up, but I know exactly what I'm doing and what parts I need and so forth. And, and it goes on, and it always goes according to plan. I've never had a case where it didn't go according to plan. So I know it's possible to come up with a plan to be able to execute it to where you can make it work if you think through it ahead of time.
Mm-hmm.
It's just going to be extremely important to do that this year.
Yeah. Okay.
And
I know one of the. Oops, sorry, Harry. I apologize.
No, go ahead. I was just going to say, and making sure everything is done and completed by the time you're ready to get out there. I've seen a lot of teams that, oh yeah, we're going to be ready to go early in the morning, and you see them for the next 3 hours drilling holes, pounding on things, and trying to get stuff to fit.
Mm-hmm. Yeah, I know one of the big things our team prides ourselves on is our checklists. Like we have our packing checklist, and then we have quality checks that we do here, and then throughout the week at launch, and then we have flight day checks. And I know those are, those are very important to us. So we definitely, I appreciate you telling us about the wind conditions and everything we can expect there, because we'll ramp those up even more before we even get out.
It's been a big issue out there this year, and there's going to be a lot of eyes looking at what the wind's doing, and people are going to make conservative decisions on the wind speed, and it's going to be tighter for 2 stages for obvious reasons.
Mm-hmm.
So you know, just, I mean, you might have a few 2 or 3 hour window in the morning when you can launch 2-stage rockets, and you got to hit it.
Okay. No, that's good to
And-
know. Thank you.
And they're also going to be making a push to get the hybrids off first thing in the mornings, also. So that's going to be interesting.
Okay.
Yes. Okay, I think the only thing left to do is to look at the recovery.
Yeah.
Real quick, if we can do that.
Yeah, we could do that. It's all set up now. So sorry it took a minute. Most of our stuff is packed up for the launch we're leaving for in a couple days. So but it's all out and ready. So okay, yeah. Do you wanna
So basically, we have our drogue set up right here and the quick links that attach to our shroud lines. And then I believe it's a 36-inch bridle between that with our swivel sitting up at the top. And then it'll separate down to the bulkhead at the motor and then the other bulkhead at our avionics bay. So those would have their quick links going to an eyeball, but
Okay, so let's look at the quick links further down there.
down here? These
Yeah.
ones?
And so you're going to be using the shock cords with the loops.
Mhm.
I mean, one thing you could do right there is just put all the loops around one quick link instead of using 3.
okay.
You know, that's just unnecessary hardware. I think there. You know, unless there's some reason to use 3, it's just more places that can get fouled.
Yeah, we can definitely look into reducing the amount that we use.
Okay, and that's the 1/2-inch giant leap.
The Kevlar, yes.
Yeah, okay. All right, well, that's the only thing I'd say about the harnesses. Just kind of make sure that they're, you know, that maybe if you have unnecessary hardware on there. I did L3 a few years ago, and I think the guy who did it probably spent, you know, $1,000 on hardware. And I mean, it was just swivel after quick link after, you know, and the harness fouled. You know, I told him it was going to do that, and it did, because there was just too much hardware on there. So it's a lesson that I've seen repeated.
No, that makes sense. I appreciate it. Yeah. We'll definitely look into reducing that.
I'm done. You guys got any questions?
No, I think you answered them all in full. We really appreciate all the help throughout today. Yeah. So I think we're all good on our end. Thank you very much.
Okay, holler if you have any questions, and otherwise we'll see you out there.
Yeah, sounds good. We will definitely be reaching out. Yeah, and excited for it. Everybody's really amped, looking forward to it. So.
Okay, I'm expecting a good launch.
Yeah, us too.
All right, very good. Thanks for going through all this, and send the link to Esra for the video. Otherwise, you'll get a nasty gram from them if they don't get a link.
Yeah, I will definitely make sure, as long as I can save this properly.
Okay.
So I will.
Yes.
Thank you guys again.
Okay, you guys have a good night.
You too. Thank you, Eric. Thank you, Jim.
Bye-bye.
Have a good